Okay, so this is a problem my students requested, and I've kind of modified it because I didn't make the original one. So let's just get to it. So here is an asteroid, and on that asteroid, and there's no reason to ask why. Some of these things just happen. Okay, on this asteroid is a rock, and you want to throw this rock as fast as you can, such that it ends up really far away with a speed of 7 meters per second. So the asteroid has a radius of 5 times 10 to the 4th meters and a mass of 5 times 10 to the 3rd kilograms. And so now the question is, how fast do you have to throw it? It's the second part of the question, but let's do the first part first. Okay, so this is a work energy problem. How do we know this is a work energy problem? Because we don't know anything about the time. And I have these non-constant forces. So once I let go of the ball and it moves up, then the gravitational force is changing as it moves up. So if you wanted to use momentum principle, it wouldn't be so easy. I mean, you could do it. It'd be tough though. Okay. So in this case, as soon as I say work energy, I need to say what my system is. This marker is not really the best. I thought I had another marker somewhere. Let me get another marker. See, a normal person would have said, hey, I'll just start the video over. No. Carry on. Keep going. Okay. So I need to pick what the system is. In this case, I'm going to say the rock plus the asteroid. And there's a reason to do that. If I pick the two objects as my system, and here let's talk about, just to be clear, v1 is the velocity right after I throw it. v2 is the velocity when it's really far away. If I pick those two as my system, then I have 0 work done. Because what's acting on that rock asteroid system as it moves further away? There's no external forces, so there's no work done. And that makes it easier. Now, but since I have the rock, I have the change in kinetic energy of the rock, I'm going to assume the asteroid does not change in kinetic energy, although it technically does. And then I have this. Change in kinetic energy plus change in gravitational potential energy. So by having the rock and the asteroid as my system, I can have that gravitational potential energy. If you don't have the asteroid in your system, you can't have that potential. You'd have to do work done by gravity, which is still get a final answer, just be a little bit harder. Okay, so let's say this is 0 equals K2 minus K1 plus U2 minus U1. So K2 is the kinetic energy when it's really far away. K1 is the kinetic energy at the beginning. U2 is the band. No, U2 is the potential energy far away. And U1 is the potential energy close up. So here, in general, kinetic energy is 1/2 mv squared. Potential energy is negative g, mass of the asteroid, mass of the rock, over the radius. Okay. So one of these terms is 0. Do you want to think which one it is? It is this one. The final potential energy is 0 because I'm going to get to a very large R. And so when R gets really large, the potential goes to 0. So let's just write this out. So this becomes 0 equals 1/2 mv2 squared minus 1/2 m, this is mass of the rock. Not the rock, Dwayne Johnson. The rock. V1, see, I like to add jokes in there so you know that I'm thinking about you. 1/2 mv1 squared, and then I have that 0, so it's going to be plus 0 minus u1, so it's going to be plus g, mass of the asteroid, mass of the rock, over the radius of the asteroid. That's where I start. The distance between these two starts at the radius of the asteroid. And now what do I want to solve for? I know V2, I know this, I want to solve for V1. Before I do that, what is the mass of the rock? Well, it doesn't matter. If I divide this side by the mass of the rock and that side, they all cancel. So now I can solve for V1. I'll skip one step. V1 squared equals, I'm going to add that to both sides. V2 squared plus G MA over R. And this is C. Got my signs right. Yes. Yes, that makes sense. So then V1 is the square root of V2 squared plus G MA over R. Okay, and I know that people get all uptight about numbers and stuff, so I'm going to put in my numbers because everyone wants a number. Okay, so I'm going to use my little Python calculator here. I'm not hiding it from you, you can see. This is just for the calculator. You can't even see that. I'll show it to you after I type it in. Okay. New trinket. Close grip. I need my gravitational constant. G 6.67 times 10 to the negative 11th. The mass of the asteroid is 5 times 10 to the third. The radius is 5 times 10 to the fourth. V2 is 7. I got everything. So I'm going to say V1 equals the square root V2 squared plus G times MA divided by R. And oh, I get 7 meters. I get 7 meters per second. Oh, I printed the wrong one. V1 is that. Why am I getting 7? V2 squared is 7 plus G 6.67 times 10 to the negative 11th MA. I think my asteroid doesn't have enough mass. Let's just change that to the 10 to the 5 times 10 to the 4th. Oh, I did. No, I'm still getting something. V1 is 7. Oh my gosh, what did I do wrong? Square root of V2 squared plus G times... 6.67. I'm getting exactly V1. Let's just take this part out. 7. Okay. Let's just put in this. G. Oh, I know what it was. Okay. I got it. V2 squared plus G times MA over R. I put GMA. And let's put this back at 5 times 10 to the third. No? MA, G, what the heck? R. Here, what's wrong with this code? Something's wrong. Oh, you can't see. Okay. I'm not sure what's going on. Let me do the second part. This is good. V2 squared G 6.67 mass of the asteroid R is 5 times 10 to the 4th. Let's just increase, let's just increase the mass to 6. It still should give me 7. What the heck? The square root of V2 squared plus G times MA divided by R. That is really weird. Sometimes you get things like this and things just don't do what you expect. Let's see, let's just print this. Print G times MA over R. That's the number. See, that's really small. So I need a much bigger mass. Let's put this at 10 to the 8th. No, still good. Okay, I don't know what's wrong. And I will figure that out and post a note or something, but I don't want to keep going on because this is already getting long. It's driving me crazy. Okay. It's a calculator problem because let's do this in Google. Okay, let's say Google, not Google Maps, it's Google. Okay, I'm going to say square root of 7 squared plus 6.67 times 10 to the negative 11 times, let's do 5e3 divided by 5e4. Oh, it is really tiny. Okay, that's the problem. My mass is super tiny and my radius is too big. Oh, this should be, let's just make this, let's make these numbers, let's make my mass 10 to the 10th, 10 to the 15th, 14th. Okay, so now if I make the mass much bigger, 10 to the 3rd kilograms, what the heck? Okay, let's make this 10 to the 13th, 10 to the 15th, 10 to the 15th, and then V1 is 7.46. Okay, that's my fault. Okay, now the question is, I don't want to throw the rock. I want to use a spring to launch it up. And so the spring looks like this. It's going to be compressed 0.5 meters. The mass of the object is 10 kilograms. And so the question is, how much, what's the spring constant for that spring going to have to be? Now, there's actually 3 positions that we have. So let me redraw this picture. So here's my asteroid. Here's the compressed mass. Here's the uncompressed mass. I'll call that V1. Let's call that V2. And that V3. Okay, so now there's 3 positions. Now I'm still going to have the system. It's going to be it's a mass plus asteroid plus a spring. So then I'm going to have spring potential energy in there. But now I have an option. What do I want to pick for my initial and starting positions? I could do 1 to 2 since I know the final velocity, or I could do 1 to 3. I'm going to do 1 to 3. So I'm going to say work is 0 is equal to delta K plus delta UG plus delta US. And so in this I have 0 equals K2 minus K1 plus U2 minus, I'm sorry, I'm calling that 3. U3 minus U1 plus US3 minus US1. Now, I have K. I have this K is 0, because now I'm starting from rest. U3 is 0, because it's really far away. And US3 is 0, because the spring's not compressed or stretched. So now I say 0 equals 1/2 m V3 squared, 0, 0, 0, minus, so plus G, mass of the asteroid, m over r. I already had that, okay? Now, I have that compression too, but it's so small compared to r, I'm just going to ignore it. And then I have minus Ks. And I know S is 0.5 meters, and I want to solve for K. So K is equal to all of this, and the side is going to be m V3 squared over 2s plus, the mass does not cancel. The mass does not cancel here. Plus G MA M over RS. So if I put in my values here, I get my spring constant, and I'm going to do that right now. So in this case, I said the mass is 10 kilograms. So S is 0.5, M is 10. So now I get K equals M times, I called it V2, V2 squared divided by 2 times S plus G times MA times M divided by R times S. And let's see if I get a value this time. K is 623 newtons per meter. Okay, I'm pretty happy. That's a pretty stiff spring, but it's doing a lot of stuff. So there you go. Apologize for my mistake, but it was a mistake. It was just using bad numbers. The end.